All right. 6.3 maximum and minimum problems using multiple variables. This is our last section. Okay, so um, just like when we did it with functions of just x and y, so like y equals something, some kind of function of x, we could find relative maximum and minimum values by taking a derivative, finding the critical numbers, and then testing around those critical numbers. Well, the testing idea it's close. It's the same general idea. We're going to find critical numbers with multiple variables. It's just going to be a little bit more algebraic work to do. And it's the same idea that we're going to take derivatives to do that. And we are still going to use second derivatives in order to figure out concavity, although I'm not going to go into the specifics about how all that's going to work. But it is going to tell us something about the concavity. And I will do my best to put up an illustration towards the end of this to at least show you kind of what it is that we're looking at graphically, because otherwise it really is kind of difficult for you to piece together what we're doing. All right, so here is the idea. In order to find relative max and mins, we do have to take first derivatives. So we need to take partial derivatives because these are functions now of x and y. And then we need to solve the system of equations that we're going to get, because we're going to get two separate equations, one with fx and one with fy. And that's going to be able to, as we solve the system of equations, we're going to be able to find the intersections of those two things, which is going to be our critical point. And then we have to do this test right here, number 3. We're going to have to evaluate this thing which is called D, which is fxx times fyy minus fxy squared. And that is something that you're going to have to know. And what that's going to tell us is this. If D is positive, D is greater than 0 after I do the number 3, then we're going to have either a local max or a local min. That's going to be dependent upon fxx. If fxx is less than 0 after we find D, then we're going to know that we have a maximum. And that's because this being less than 0, fxx being less than 0, would actually indicate at that point the curve or the surface of this thing is concave down. So it would look like that. Then if we get D to be positive and fxx is also positive, then it would be concave up, meaning at the bottom of the hill you would have a minimum. If D itself, which is different, is less than 0, so if we get a negative D value, we have what is called a saddle point, and that's something that I'm going to have to illustrate for you in that graph. And a saddle point is neither a maximum or minimum. Again, hopefully when I show you the graph, you're going to understand what I mean by that. If D equals 0, which is not going to happen in any of our problems, this test is not applicable. You'd have to try something else. But that won't happen in any of our stuff. All right, let's get to it. There's only 3 examples because these can take some time to do. So again, if this goes a little too fast for you, please go back, watch it again, make sure you understand how all of this works. In order to find critical values, I need to take fx, f sub x. That's the partial derivative of this thing with respect to x. Well, x squared, the derivative is 2x. The derivative of xy, remember that y is a constant, so that is just going to be y. The derivative of y squared and negative 5y, those are 0 because y's are constant. I'm also going to need the partial with respect to y. X squared, that's nothing because x is constant when you take the derivative with respect to y. The derivative of xy is x. Derivative of y squared will be 2y. And the derivative of minus 5y will just be minus 5. Remember, that's only with respect to y. So, in order for a critical value to give you a critical point, you have to set it equal to 0. So we'll set that equal to 0. Now I am going to solve this for y, which means I'm just going to subtract 2x on both sides. And since this is a system of equations, this one also must equal 0. But now what I have by doing the one on the left is I have an expression, negative 2x, that I can substitute into the y value right there because that's what y is. So then I get x plus 2 times negative 2x minus 5 equals 0. Now I can solve that for x. So that's going to be x minus 4x minus 5 equals 0. So that's going to be negative 3x minus 5 equals 0, adding 5, and then dividing by 3 gives you x is negative 5/3. Okay, that is the x value of my critical point, but it's a critical point, so I need the y value. So I'm going to take that 5/3 and I am going to plug that back in here for x. So then the y value of my critical point would be negative 10/3. So after all that, my critical point is going to be the point negative 5/3. That is supposed to be a 5. Negative 10/3. That's my critical point. Now what I have to do is I have to see whether this critical point is a maximum, a minimum, or neither. It could be a saddle point. So let's check it out. According to what we have up here, we need to find this. And that's going to tell us what we have to start with. So I need fxx, I need fyy, and I need fxy. Remember that fxy and fyx are going to be the same. So let's find fxx first. That is the derivative of this guy right here with respect to x only. Well, that's just going to be 2. I need fyy, which is the derivative of fy with respect to y. That is also just 2. And then I need fyx and fxy. So let's see. fxy, which will equal fyx, and we can double check that just to make sure that this is the case. The derivative of this thing now with respect to y is 1. The derivative of this thing now with respect to x is also 1. So those two things work out. So now d, and this is the important part, is fxx times fyy minus fxy, that whole thing, squared. So let's see what we get. Well, fxx is 2, fyy is 2, minus fxy, which is 1 squared, that's 1. So 4 minus 1 is 3. That is greater than 0. And since this is greater than 0, I'm going to have a max or a min according to the criteria above. We just have to figure out which one it is. Well, what tells us that is the sign of fxx. fxx is 2, which is greater than 0. So really that means it's opening up. So that means that we have a minimum. So what we need to do now is we actually need to find that minimum. And this is where you're probably going to need your calculator, because to find the minimum, you're going to have to plug this critical point back into the original equation. So f of negative 5/3, negative 10/3 is going to actually give you the minimum value. It'll basically give you the function's value. And I've already done that, and assuming that I did it right, I got negative 25/3. That is the minimum of this function at that critical value. All right, let's go ahead and go on to the second page. And again, I am going through these things probably more quickly than I probably should, but I only have a certain amount of time for the video, so I want to make sure I get that in. Again, go back and watch it again if you need to. All right, number 16, a concert promoter produces two kinds of souvenir shirts. Total revenue from the sale of X thousand shirts at $18 each and Y thousand at $25 each is given by R of XY. That's your revenue, equals 18X plus 25Y. The company determines that the cost in thousands of dollars of producing X thousand of the $18 shirt and Y thousand of the $25 shirt is given by the cost function, which is there. How many of each shirt must be produced and sold to maximize profit? Well, remember that profit of these two shirts is revenue. Oops, this should be revenue of XY. Forgot we're in two variables. Minus cost. So the first thing I have to do is set up the profit equation. That is revenue minus the cost. Cost is a very lengthy function. Make sure you put it in parentheses, otherwise you might forget to distribute the negative to everything. That is really long. I am going to take the derivative and distribute the negative at the same time. Please distribute the negative first if that is going to be too much for you to see. So go ahead and do that on your own. Distribute the negative through everything, basically changing every sign inside the parentheses if you need to do that. We are trying to maximize this profit, so I need P sub x because I'm going to find the critical values first. So P sub x is going to be, let's see, 18. 25y is nothing. The next one is going to be minus 8x. I am distributing the negative. Plus 6y. The 3y squared has nothing to do with x. The next one will be minus 20. And then I have no more x's throughout. So I can combine some like terms here. So that's going to be minus 8x plus 6y minus 2, that looks right, and that's got to equal 0. Let's do P sub y. Partial with respect to y, the 18x is nothing, 25y is 25. Okay, the 4x squared is nothing. I do have to do the 6xy, so that's going to be plus 6x with respect to y. And then the 3y squared is going to be minus 6y. Again, I am distributing the negative as I go. 20x is gone. Then we'll have minus 19, and then the 12 is gone. So let's combine whatever like terms we can there. 6 plus 6x minus 6y equals 0. Okay, now what I have is I have two functions. I could solve one of them for x or y and plug it into the other one. There's a second way to do a system of equations, and I'm going to do it this way just to make sure that you guys remember both ways. And you could do any of these in this way, by the way, as long as they're both linear, and they are. I'm going to, on the green one, I'm going to add the 2 to the right. And on the red one, I'm going to subtract the 6. Now what I have is a system of equations which I can set up as negative 8x from the green one, and then from the red one, and hopefully you remember this is a process which is called elimination. You can add these two things up, and adding straight down negative 8x and 6x is negative 2x. 6y and negative 6y is 0. This is good. We needed one of those to go away. And then 2 and negative 6 is negative 4. So solving that for x, dividing both sides by negative 2, you get x equals 2. And then I need to plug 2 back in. It doesn't matter. I can plug it back into either one of these two equations right here to find y. I'm not going to walk through that one with you guys, but the y value, if you plug 2, and it'll work for both of them, by the way. If you plug 2 back in, you should get out y equals 3. And you can double check that just to make sure, but that should be the y value. So that gives me my critical point. My critical point is 2, 3. I now need to check to see whether that is a maximum or a minimum, because we are trying to maximize profit. So hopefully this is where it's going to be a maximum. So let's check it out. I need PXX, I need PYY, and I'm also going to need PXY, which is the same as that doesn't look good, which is the same as PYX. They are the same. All right, so let's find it. PXX, the derivative of this guy right here with respect to x. That's just going to be -8, looks like. Yep, because the only thing that has x in is that -8x. PYY, so the derivative of this one with respect to y, the only thing that has y in it is that -6y, so the derivative of that is -6. And then PXY, so the derivative of the green one with respect to y is 6. So PXX, PYY, so we got to do D, PXX times PYY minus PXY squared. Well, that's going to be 48 minus 36 is 12. That is a number which is greater than 0, which means we do have a max or minimum, and PXX is negative because it's -8. That means that this thing is concave down, so we do indeed have a maximum. So we have a max at f of 2, 3, and if I plug 2 and 3, well, actually it's not even asking me for that, is it? It just says how many of each type of shirt. Well, according to this, I need to sell 2, and this is in thousands, so I need to sell 2,000 of the X shirt, 2,000 X shirts, and 3,000 Y shirts to maximize the profit. You could find that by plugging those back into your profit equation. You could actually find what the profit is, but we don't need to. Not asked. So I don't need to worry about that. It did ask me how many shirts. So that's how much is going to maximize the profit. Okay, one more problem. Let's see if we can get this done in under 30 minutes total. I think I can. All right. Find the relative maximum and minimum values as well as any saddle points. So it's just straightforward like the first one as far as finding the critical values and then seeing if it's a max, min, or saddle. No word problem here. So same process. We need fx, which is going to be, in this case, the 2y squared is 0, so the derivative of x squared is 2x. X squared y is going to be minus 2xy, and that has to equal 0. And then we have to do fy. With respect to y, that'll be 4y. The x squared part is gone. The x squared y is going to give me minus x squared. So I'm going to solve the one on the left. And by the way, it doesn't matter. You can solve either one, but the one on the left looks easier to me. So it'll be 2x equals 2xy. If I divide 2x on both sides, I get y equals 1. And since I know that y equals 1, I'm going to plug 1 into the equation over here, equals 0. So that'll be 4 times 1 minus x squared equals 0. Well, that's 4 minus x squared equals 0. If I add x squared to both sides and then take the square root, I get that x has to equal plus or minus 2. Well, that's interesting because that means that x is positive 2 or x is negative 2. Both of those go with a y value of 1. So I actually have two critical points. So I have a critical point at the point 2, 1. I also have a critical point at -2, 1. So I have two critical points here to find. Okay, we still need to do the process that we did before. We need fxx. So that's the derivative of fx with respect to x only. So that's going to be 2 minus 2y. We need fyy, which is the derivative of y with respect to y. Again, well, that's just 4. And then I need fxy, which again is the same as fyx. So it's the derivative of this one with respect to y now. So that's just going to be minus 2x. Now this is different in the fact that now I still have variables left over in these, so I actually have to plug in the critical points in order to find this. So a lot of people make a chart out of this, which you can do. I'm going to kind of show you what I mean by that. So this is our D chart. So we're going to have our critical value, 2, 1, negative 2, 1. And we're going to find D. We're going to do fxx right here, evaluated at the critical point. We're going to do fyy right here, and we're going to do fxy right here. So remember that you are multiplying those, and you're going to subtract the square of that one. And then we're going to see what our D value is. So fxx, that's this one, evaluated at the first critical point, which is that one. Well, I only have a y to plug it into. So if I plug 1 into that y, I'm going to get 2 minus 2, which is 0. So really, it's not going to matter what fyy gives us here. But fyy is 4 minus fxy squared. Well, that's the negative 2x part, and I can plug a negative 2, I can plug 2 into that for my critical value, so that's going to be minus 4 squared. So ultimately, that's going to give me 0 times 4, which is 0, minus negative 4 squared, which is 16. That gives me negative 16. That's less than 0. I don't have anything else to do. That is what's called a saddle point. And again, I will have to illustrate that so you can see what that looks like. Let's try the same thing now with negative 2, 1. If I plug negative 2 into fxx, sorry, 1 into fxx, it's also going to give me 0, and then 4 is still fyy regardless, minus negative 2 times negative 2 will give me 4 squared. It's ironically going to give me the same thing. 0 minus 16 equals negative 16. That's less than 0. That's also going to give us a saddle point. So to find the actual saddle points, we have to take 2, 1 and negative 2, 1 and plug those back into the original equation at the top. And again, I've already done all that, so my saddle points are f of 2, 1 equals 2, and ironically, f of negative 2, 1 also equals 2. All right, that's the math behind it. Now I want to take a second, and I'm going to have to pause my video, although it won't really seem like it to you guys, and I'm going to try and pull up a graph of this so you can see what this looks like, and I will show you what a saddle point means. All right, so what you see here is a three-dimensional graph of the function that we actually just found the saddle points on. What I'm hoping that you guys can see, and I can't really touch this because it's going to move until I try it, is at the bottom here there are these two black dots. If you can kind of see, like, it goes up and then comes down and then goes up and it comes down under the white. There's two black dots underneath of this thing. That would look like it would be at a maximum because it looks like it goes up and it comes down. But if I turn this thing and look at it three-dimensionally, let's see if I can do this. Oh, I'm trying. Here's one of our, oh, this is so hard to do. Here's one of our black dots. Oh, it's moving all over the place. I apologize. One of the black dots is on the inside here. You know what? I'm going to try and do this another way. I'll try and do this while I sit at the computer as opposed to where I have it right now. Just got to make my way over to the computer. So here I can use the mouse. Now so there's a black dot right here. Now it looks like this is at a minimum. See how it comes down and then back up? But then when I turn it to the side, now we're back to it. Now it looks like a maximum. So it goes up and then down here, and then up and then down here. That looks like a maximum, but when I keep turning it to the side, if I look at it from a different angle, from this part, this comes down and it goes back up. Basically, if you think about it, this is actually what it looks. This is kind of skinny, but it looks like a saddle. You could sit in the middle of this. Your legs could drape over the side, and it looks like a saddle. That's why they call it a saddle point. So from one perspective, it's at a max. From the other perspective, it's at a min. So that's what a saddle point is geometrically. All right, that's probably enough. Got it done in under 30 minutes. So enjoy, and that's it.